Time slips through every experience we have, yet remains the one element we never truly grasp. We speak of it as if it were a flowing river, carrying us from one moment to the next. We imagine ourselves drifting within its current, but physics tells a different story. In the language of physics, time is not a river, it is not a force, it is not a thing that pushes or pulls. Instead, it is a coordinate, a place, a label we attach to events so that we can say one happened before another. In the same way that you can point to a location in space, physics allows you to point to a location in time. This idea, at first glance, feels almost disappointing, almost too cold to match the vivid sensation of moments slipping away. Yet this is exactly what the equations say. Time is simply another axis in the grand geometry of the cosmos. To understand this, imagine the entire universe frozen in a picture. Not a snapshot of space alone, but a snapshot of space and time together. Everything that has ever happened and everything that will ever happen is embedded in this four-dimensional structure that physicists call space-time. In this picture, there is no motion, there is no flow, there is only the vast tapestry of events laid out in a complete whole. You can trace your own life as a long line within it, beginning with your birth and stretching toward your future. You might think of this line as a journey. The equations prefer to think of it as a path that simply exists all at once. This does not mean that your experience of living moment by moment is an illusion. It means that your subjective experience of passage is something that arises from the inside rather than being imposed from the outside. The laws of physics do not demand that time moves. They only require that systems evolve according to rules that relate one coordinate to another. The sense of flow is something your mind constructs as it processes change. It is a story your consciousness tells itself to organize memories and perceptions. This becomes even more striking when we consider Einstein relativity. Relativity teaches that there is no universal now. There is no cosmic clock ticking away for everyone. Two observers moving relative to each other will disagree about which events happen at the same moment. What one person calls the present might be considered part of the past or future by someone else depending on how they move. This is not speculation. It is an experimentally verified fact. The absence of a privileged now means that the universe does not single out any particular moment as special. Every slice of time is equally real. The idea that now is not universal may feel disturbing because our psychological sense of presence is so strong. When you are aware of something, you feel that awareness has a sharp edge separating past from future. You feel that there is a boundary where potential becomes real. But physics says that boundary is different for every observer, and that none of these boundaries define a feature of the universe itself. They only reveal how each observer moves through space-time. Despite all this, despite the cold clarity of the mathematics, your experience fights back. You feel time moving forward. You feel anticipation when you look ahead, and memory when you look behind. You know the past, but never the future. You age, and nothing ever unages. You watch smoke spread through a room and never watch it gather into a neat column again. You can scramble an egg, but cannot unscramble it. You see stars burn their fuel and never reignite in reverse. Everyday experience insists that time flows in one specific direction. It insists that the universe pushes us forward rather than backward. This tension lies at the heart of one of the deepest puzzles in science. The fundamental laws of nature appear to allow processes to run forward or backward. If you were to watch a film of two billiard balls colliding and you played that film in reverse, the reversed motion would still obey the laws of physics perfectly. Nothing in those laws would forbid the backward version. Yet we never see glasses that leap up from the floor and reassemble themselves. We do not encounter rivers running from the sea back to mountain springs. Our reality is soaked in a one-way direction. So what creates this direction? What gives rise to the arrow of time that our senses cannot escape? If time itself does not flow, if the universe does not include a universal now, And if the equations do not prefer forward over backward, then how does our world acquire such a strong and unbreakable sense of temporal order? These questions force us to peel away the layers of everyday intuition and look at the universe through a sharper lens. The answer does not lie in psychology alone. It emerges from the structure of physical law and the way the cosmos began. And while modern physics offers profound insights into these mysteries, it also reveals new puzzles. When we chase the arrow of time to its origins, we discover that the universe is far stranger than our instincts ever imagined. The journey begins with a rule that seems simple, yet shapes everything we see. It is a rule that breaks the perfect symmetry of time in the real world. It tells us why ice melts, why stars shine, why moments pass, and why your memories face one direction. It is the rule that takes a universe full of reversible laws and turns them into an irreversible story. Time feels intimate. It sits inside every heartbeat, every breath, every shift of sunlight across a room. It shapes the rhythm of a life, even though nothing in the equations of nature acknowledges this rhythm. The laws governing particles and fields operate without caring which direction time points. They lay out possibilities in elegant patterns that can run forward or backward with equal mathematical ease. Yet the universe we inhabit refuses to behave like a reversible pattern. It behaves instead like a story moving relentlessly toward what we call the future. Understanding this contradiction means recognizing that there are two versions of time. One is the time of physics, which is simply a coordinate. The other is the time of experience, which feels like motion. The tension between these two forms of time is not a flaw in our understanding. It is a clue. When you look at the stars across the night sky, you know you are seeing light that left them long ago. In some cases, the light began its journey hundreds of thousands of years before humanity even took shape. Yet the moment you see that ancient light feels like the present. This is because your brain stitches together the signals reaching your eyes and ears and gives you a sense of presence. It is your brain that tells you things are happening now. Without that internal stitching, time would appear much more like the structure that physics describes. It would feel static. It would feel like a complete tapestry where every event has its assigned place and no event is more real than another. The sensation of flow comes from memory. You remember what happened a moment ago, and you predict what may happen a moment from now. This creates a moving window of awareness. Memory is always about what came before, and prediction is always about what might come next. When these two processes interact inside the mind, consciousness interprets the difference between them as a passage of time. Your awareness slides along the timeline, even though nothing in the timeline itself is moving. The movement is internal. It is a construct produced by the way biological systems process information. Still, no matter how clearly we describe this in scientific terms, time refuses to feel like an illusion. You feel yourself aging. You feel moments falling away behind you. You feel the certainty of irreversible change. Even when physics shows that the laws allow both directions equally, your life unfolds only in one. This is not because of relativity. Relativity takes away the idea of a universal now, but it does not create a direction. It simply tells us that different observers slice space-time differently. The arrow of time is deeper than that. It is older than the stars. It is carved into the universe itself. Imagine watching a glass fall from a table. The fall is simple. The shattering is chaotic. Pieces scatter across the floor, each following a trajectory that seems random. Yet if we imagine the same event in reverse, the randomness becomes impossibly coordinated. Shards slide back together with perfect precision. Light recombines. Sound waves converge, and the glass leaps upward. The film looks magical. The laws of physics do not forbid the reversed motion. They simply describe it as highly improbable. And improbability is where the arrow of time begins to whisper its presence. Your daily life is filled with events that become more disordered over time. Smoke spreads through a room. Ice melts into water. Heat diffuses, stars exhaust their fuel, clouds form from turbulent air. Every one of these processes is biased towards states that are less organized. This does not violate the fundamental rules of motion. It emerges from the way large collections of particles behave statistically. The deeper we study this, the clearer it becomes that the arrow of time is tied to the growth of disorder in the universe. But disorder alone cannot create direction. There must be a starting point that is special, a moment when the universe was arranged in a way that allowed disorder to grow. This is where cosmology enters the story. When we trace the universe backward in time, we find that it becomes hotter and denser as we approach its origin. The early universe was filled with a nearly uniform sea of radiation and matter. That smoothness might sound like a kind of chaos, but in the language of physics, it is the opposite. Smoothness means low gravitational entropy, which means low disorder. The universe in its infancy was extraordinarily ordered. It began in a state so special that it allows entropy to rise everywhere and at every moment. This origin is the key that ties together the time of physics, the time of consciousness, and the time of experience. Without a low entropy beginning, the arrow of time would not exist. We would not have memories pointing one direction. We would not have broken glasses or melting ice. We would not have galaxies or stars or planets. The universe would be a frozen geometry where nothing irreversible occurs and nothing evolves. The early universe did not just give rise to matter and energy. It gave rise to direction. It seeded the difference between past and future. And because that seed was planted at the very beginning, the arrow of time pervades the entire cosmos. It is not a choice made by the laws of physics. It is a consequence of how the universe started. The flow you feel inside your mind mirrors the growth of entropy around you. Your memories face one way because the cosmos itself is unfolding in that same direction. We have not yet explored what entropy truly means or why its increase appears so universal. We have not examined the rule that breaks the symmetry of time in our lived reality. That rule is the thermodynamic arrow, and understanding it is the next step in unraveling the mystery of why the universe moves forward. The more closely we examine time, the more it seems to divide itself into two layers. One layer is the silent geometry of space-time, where events simply exist. The other is the animated world we live inside, where moments unfold in a sequence that feels both natural and unavoidable. These two layers are not enemies. They are companions. One describes the structure of reality. The other describes the way complex systems inside that reality behave. When we observe the sky, when we walk across a room, when we watch steam curl from a cup, we are seeing the world through the second layer. We are seeing processes that depend on change, and change depends on a direction. Think of a simple example. Imagine an ice cube resting in a warm room. The molecules inside the cube begin in a tight and rigid structure. As heat flows in, the structure loosens and water forms. If we were to look only at the molecule positions without knowing the direction of time, we could, in principle, run the motion backward. But the backward motion would show water spontaneously forming a perfectly shaped crystal, while heat flows out into the room. That is not impossible in the sense of physical laws. It is impossible in the sense of probability. The number of microscopic arrangements leading to a melted state is vastly greater than the number that produce an orderly solid. This difference in possibilities is why melting feels natural and freezing without energy removal feels absurd. The word natural is misleading here. Nature does not have preferences. It follows rules. One of those rules, perhaps the most important for understanding time, is that systems tend to move towards states that can be realized in more ways. A broken glass can be arranged in a huge number of possible shard configurations. An intact glass can only be arranged in a very small number. When systems evolve according to blind mechanical interactions, they drift toward the states that are statistically favored. This drift is what we call the increase of entropy. It is not a force pushing things forward. It is the outcome of counting possibilities. Yet this raises a deeper question. If states of higher entropy are so overwhelmingly likely, why was the universe ever in a low entropy condition to begin with? Why did the cosmos start in a state so smooth and so orderly that it allowed entropy to rise for billions upon billions of years? This is one of the greatest mysteries in science. It links the arrow of time to the earliest moments of existence. It hints that the direction we experience now may have been set at the instant the universe emerged. To approach this mystery, imagine the early cosmos as a vast, uniform fog of matter and light. That uniformity looks simple, but it represents an extraordinary level of gravitational order. Gravity prefers clumps, not smoothness. A universe filled with evenly spread matter is an improbable arrangement when compared with a universe filled with stars, galaxies, and black holes. In fact, the formation of galaxies marks a dramatic rise in gravitational entropy. Clumps form because gravity pulls inhomogeneities together. As they collapse, they create deeper wells of gravitational potential. This opens the door to more configurations, and therefore to more entropy. This means the early universe was not just hot and dense. It was structured in a way that allowed gravity to do creative work. The growth of structure is a climb up the ladder of gravitational entropy. Stars ignite, planets form, black holes gather unimaginable amounts of mass into tiny regions. Each stage increases the number of possible microscopic arrangements. Each stage reinforces the arrow of time. If the universe had begun in a messy and disordered state, entropy would not have room to increase. Time would not have direction. The cosmos would have lacked a gradient for irreversible processes to follow. From this perspective, our personal sense of moving from past to future is tied to events that unfolded long before life appeared. The low entropy beginning created a universe in which clouds could collapse, elements could form, planets could accrete, and evolution could take place. Every breath you take is shaped by the ancient imbalance that made time directional. Every memory you hold is made possible by the fact that entropy increases. If the early universe had been different, consciousness itself might never have emerged, because there would be no arrow for memory to align with. Understanding time requires us to see ourselves as part of this cosmic chain. We live inside a universe that started in a state so special that it permits direction. Our lives unfold along that direction. We sense it internally because we are built from matter that obeys thermodynamic rules. When our neurons store memories, they increase entropy. When we perceive change, we are registering the difference between more ordered and less ordered states. The arrow of time is not only around us, it is inside us. And yet, the fundamental laws still do not choose a direction. They remain elegantly symmetric. They allow processes to run either way. The arrow emerges only when we consider statistics, probabilities, and the history of the cosmos. To understand why time feels so forceful and so absolute, we must next explore the rule that breaks that symmetry in practice. We must look at entropy itself, how it grows, why it grows, and why this growth defines the difference between what we call the past and what we call the future. The universe appears calm on the surface. Stars shimmer in the night and planets orbit in predictable cycles. Yet beneath this orderly dance lies a deeper truth. Everything around us drifts from states of greater order towards states of greater disorder. This drift is not caused by a hidden push. It is not the result of a cosmic preference. It arises because the number of ways to be disordered far exceeds the number of ways to be ordered. And this overwhelming imbalance creates the phenomenon we call the arrow of time. It is the quiet rule that breaks the perfect symmetry of the fundamental laws. It explains why ice melts, why smoke spreads, and why memories form in only one direction and never the other. To grasp this fully, imagine a deck of cards laid neatly in sequence. That sequence represents a highly ordered state. If you shuffle the deck once, you are very likely to produce a random arrangement because the number of random arrangements dwarfs the number of ordered ones. If you shuffle again, the deck does not return to its perfect order. You would need an astronomically long sequence of perfectly chosen shuffles to recreate that structure. The physics of molecules behaves the same way. Ordered states are rare, disordered states are plentiful. Left alone, every system tends to wander toward the vast ocean of possibilities rather than the narrow channel of precision. This wandering is entropy increasing. Entropy is often described as disorder, but the word disorder can be misleading. Entropy is more accurately the count of how many microscopic ways a system can occupy its current condition. A neat room can only be arranged in a few precise ways. A messy room can be arranged in enormous numbers of ways. A neatly stacked library of data stored in a computer has only a few configurations representing the same information. When the data becomes corrupted, the number of possible corrupted arrangements is enormously larger. Entropy is not a force, it is a measure. It is the language through which nature counts possibilities. This simple counting explains why broken glasses do not reassemble themselves. The shards on the floor represent an enormous number of possible microscopic states. The original glass represents a tiny number. Even though the fundamental laws could run backward, the probability of every atom moving in precisely the right direction to restore the glass is so small that it might as well be zero. That improbability becomes the foundation of irreversibility. It becomes the reason processes unfold with a direction. It becomes the arrow of time. The remarkable thing is that this arrow does not contradict the deeper symmetries of physics. The laws governing particles and fields do not contain instructions forcing them to move forward in time. They allow future and past to be treated on equal footing. But when billions of particles interact, the statistics of their motion overwhelmingly favor one direction. This is where symmetry meets experience. The underlying rules are reversible. The patterns that emerge from the collection of particles are not. Consider the flow of heat. When a warm object touches a cold one, energy migrates from the warm object to the cold one. This always happens in the same direction. We never see heat gather itself spontaneously in one small region. The reason is simple. There are far more ways for energy to spread out than to clump together. Spreading is the natural consequence of probability. Clumping is the improbable outcome. So when heat diffuses, entropy rises. When ice melts in a cup, entropy rises. When steam fills a room, entropy rises. The universe leans toward the configurations that can happen in countless ways. This universal leaning raises profound questions. Where did the pattern begin? Why did the cosmos start in a state that allowed entropy to increase so effortlessly? What made the earliest moments so orderly that the later growth of disorder became inevitable? Answers to these questions require us to examine the birth of the universe itself. The thermodynamic arrow of time cannot be understood without tracing its roots back to the conditions that existed before galaxies formed, before atoms assembled, even before the first light traveled across space. Entropy is the quiet sculptor of direction. It shapes the story of the universe without violating the fundamental laws. It tells us why we age, why processes unfold in only one orientation, and why the future feels open while the past feels fixed. Yet to see the full picture, we must go deeper. We must ask why the universe began in a state so special that it guaranteed the growth of disorder everywhere and at every moment. The answer to that question takes us back to the dawn of time, when the cosmos emerged in a form far smoother and far more structured than we would expect from chance alone. Entropy is often imagined as a kind of destruction, as if the universe prefers to break things rather than assemble them. But entropy is not destruction. It is simply possibility. A snowflake has an intricate pattern that can only be constructed in a limited range of ways, but a puddle of water can take on an immense variety of microscopic forms. When the snowflake melts, the universe is not erasing beauty, it is moving toward a state that can be realized through far more microscopic arrangements. The laws governing molecules do not choose to melt the snowflake. They simply follow the path that passes through the greatest number of hidden possibilities. This becomes even clearer when we consider an everyday example. Imagine a cup of tea sitting on a table. For a brief moment after it is poured, the surface is smooth and still. Then the faintest swirl appears. That swirl breaks into smaller and smaller motions. Heat flows outward. The aroma spreads into the air. The once structured arrangement of hot fluid becomes a shifting sea of molecules exploring every possible path. Nothing forces this motion to go one way. The molecules could in theory move in reverse and cause the tea to become perfectly still again. But the number of microscopic configurations representing calm perfection is vanishingly small. The number representing agitation is astronomically vast. The universe naturally moves toward the larger set. This is why symmetry is broken in practice, even though it remains unbroken in principle. The fundamental laws can trace motion backward. They can describe a world where steam gathers itself, where atoms drift inward to form ice without the removal of heat, where broken pottery leaps upward and restores itself with effortless grace. But these worlds exist only as mathematical possibilities. In the realm of actual events, probability rules. Large numbers of particles act together to create overwhelmingly one-sided outcomes. These outcomes define the arrow of time. The arrow is not carved into the equations. It is carved into the statistics of systems containing many interacting components. If we lived in a universe containing only two particles floating alone in empty space, we would not feel a direction. The motions of those particles would trace their paths according to the reversible mathematical rules we can write down on paper. There would be no melting, no cooling, no aging. There would be only geometry. The arrow of time requires complexity. It requires countless particles colliding, exchanging energy, and exploring a vast landscape of configurations. Many people imagine entropy as a giant cosmic trend toward uniformity, but this is not quite right. Entropy does not mean sameness. It means an increase in the number of ways the parts of a system can be arranged while still producing the same overall appearance. A cloud drifting across a mountain valley has immense entropy because there are enormous numbers of microscopic ways for air and water molecules to create that shape. When the cloud dissolves into the sky, its entropy grows even more because the number of possible arrangements becomes greater still. The appearance becomes simpler, but the underlying possibilities expand. This idea becomes more powerful when we extend it beyond everyday experiences and apply it to the universe as a whole. If entropy is the measure of how many microscopic states match a given macroscopic appearance, then the early universe forces us to ask a startling question. Why was that early state so smooth? Why was matter spread almost evenly across space rather than gathered into dense clumps? From a thermodynamic perspective, the smooth state seems high in entropy because it looks uniform, but from a gravitational perspective, the smooth state is extremely low in entropy because gravity favors clumpiness. A universe filled with black holes has far more gravitational entropy than a uniform fog of matter. This means the universe began in a very special condition, a condition so special that gravity had tremendous room to increase entropy by forming stars, galaxies, and eventually the colossal black holes that dominate the entropy budget of the cosmos. Without this early smoothness, entropy would not rise. The arrow of time would not exist. The laws of physics would still be reversible, but nothing would unfold with direction. The cosmos would be static in its behavior even as it extended in four-dimensional space-time. The fact that the universe began smooth is one of the great clues in physics. It suggests that the arrow of time is tied not only to thermodynamics, but also to the birth conditions of the cosmos itself. It suggests that the direction we feel in every heartbeat, every thought, and every irreversible process is a direct consequence of the way the universe emerged from its primordial beginning. The expansion of space, the growth of structure, the cooling of matter, the formation of atoms, all of these events reflect the same underlying truth. Entropy increases because it began incredibly low. When we open a physics textbook, we might see entropy defined in neat sentences or concise equations. Yet those expressions cannot fully convey the profound narrative unfolding across cosmic history. Entropy is the storyteller behind the formation of galaxies. It is the quiet force behind the cooling of the cosmic microwave background. It guides the collapse of gas clouds, the ignition of stars, and the eventual consumption of matter by black holes. It governs the irreversible evolution of biological life. It shapes memory, learning, and even the directionality of consciousness. To appreciate the full weight of entropy is to understand that the arrow of time is not a preference of the laws of nature. It is the natural outcome of starting conditions that favored an enormous growth of possibilities. The universe began in a state that allowed complexity to flourish. And as complexity flourishes, irreversibility rises with it. The future feels open because so many possible paths lie ahead. The past feels fixed because the number of ways to return to it is minuscule. Entropy acts as the architect of what we experience as flow. Our next step is to trace this story backward to the earliest moments of existence. Only by understanding the special conditions at the origin of the cosmos can we see why entropy had room to grow and why the arrow of time became unavoidable. The universe did not simply expand. It expanded from a state that embedded direction into its very fabric. To understand the arrow of time at its deepest level, we must follow entropy back to the point where the universe first came into being. Every irreversible process around us, from the slow cooling of a star to the unraveling of a thought inside the human mind, traces its ancestry to an initial state so smooth and ordered that it stands out as one of the greatest cosmic enigmas. The early universe was hot, dense, and filled with radiation, yet in the language of gravitational entropy it was astonishingly low in disorder. This contrast between heat and gravitational smoothness is not intuitive. Heat suggests chaos. Smoothness suggests uniformity, but gravity speaks a different language from thermodynamics. To gravity, lumps represent disorder. A completely smooth distribution represents a precise and delicate arrangement. Imagine a vast landscape. In one version of that landscape, mountains and valleys scatter across the terrain in all directions. In another version, the land is perfectly flattened, with not a single deviation from absolute levelness. The flat landscape is far more ordered. It requires precision. The chaotic landscape, with all its fluctuations, can be created in countless ways. The early universe was like the flat landscape, smooth beyond anything we would expect from random chance. So smooth, in fact, that it demands explanation. When matter is smooth, gravity has room to grow structure. It has room to pull regions inward, to shape galaxies, to forge stars, to ignite furnaces that will shine across billions of years. Each of these processes increases gravitational entropy dramatically. When galaxies form, the number of possible microscopic arrangements multiplies beyond comprehension. When stars are born, matter collapses into dense, organized, glowing spheres. And when black holes form, the entropy of the universe leaps upward by staggering amounts. A black hole with the mass of a single star already contains more entropy than all the ordinary matter in an entire galaxy. A black hole with the mass of a billion suns contains more entropy than the combined chaos of countless galactic systems. The early universe contained none of these high-entropy objects. It was smooth. It was structured. It was poised at the edge of enormous possibility. This initial smoothness is what made the universe directional. Without it, gravity would not have created structure. Stars would not have ignited. Planets would not have accreted. Chemistry would not have taken root. Life would not have evolved. Memory would not have formed. Every irreversible phenomenon depends on the universe beginning far from equilibrium. Entropy needs room to climb. Time needs room to gain its arrow. The early universe created that room. Yet this realization raises a profound question. Why did the universe begin in such a low entropy state? Why was it not born chaotic? If disorder is overwhelmingly more likely than order, why did the cosmos start at the rarest end of the spectrum? The question remains one of the deepest unsolved mysteries in modern cosmology. Many theories attempt to explain it. Some suggest that inflation, the exponential stretching of space in the earliest fractions of a moment, smoothed the universe into its uniform state. Others propose that deeper principles, not yet understood, determined the initial conditions. But none of these possibilities eliminate the mystery entirely. They simply move the question one step earlier. No matter what mathematical structure we imagine, the fact remains that we exist in a universe where entropy was once incredibly low and has been rising ever since. The arrow of time is not rooted in the equations themselves. It is rooted in the starting point of the cosmos. The fundamental laws permit a universe without direction, but the initial arrangement of matter ensured that direction would arise. From that moment onward, every process unfolded along a one-way path defined by the growth of entropy. This one-way path shapes every aspect of daily life. The cooling of a cup of tea, the aging of a star, the decay of radioactive atoms, the formation of memories inside neural tissue, each follows the same general rule. They move towards states with more microscopic possibilities, never towards states with fewer. The entire world feels the arrow of time because entropy increases everywhere it is free to increase. And entropy is free to increase because the cosmos began in a state where its growth was allowed and even inevitable. When seen from this perspective, the arrow of time is not a cosmic force pulling us forward. It is a consequence of starting at a specific point in a vast landscape of possible states. It is the statistical fallout of beginning in an extraordinarily special configuration. The universe does not insist that time flow in one direction. It merely allows processes to evolve. Their evolution reveals the arrow. The next step in unraveling this grand narrative is to peer deeper into the moment when the universe began, to understand how such smoothness came to be, to explore why the early cosmos possessed the special conditions that allowed the thermodynamic arrow to take hold. Only by venturing back into those earliest instants can we see how the directionality of time was inscribed into the fabric of existence. The beginning of the cosmos is not merely an opening scene. It is the foundation from which every irreversible process, every rising entropy pattern, and every sensation of time's direction emerges. To understand why the universe feels like it moves forward, we must look back to the moment when everything known, everything seen, and everything imaginable was compressed into a state so extraordinary that nearly all of modern physics still strains to describe it. This early state was not merely dense and hot, it was exquisitely smooth, almost perfectly uniform, a condition so special and so improbable that it remains one of the great mysteries in science. That smoothness is the key to understanding the thermodynamic arrow of time. Imagine for a moment the earliest cosmos, only a breath after its birth. Space was filled with radiation and elementary particles interacting at temperatures so intense that even atomic nuclei could not hold themselves together. Yet this searing ocean of energy was not turbulent. It was not filled with swirls or clumps or chaotic structures. Instead, it was astonishingly even, like a perfectly calm sea stretched across the entire observable universe. This uniformity is measured today in the cosmic microwave background, the leftover glow from the universe youth. The temperature variations across that ancient light are tiny, only a few parts in 100,000 when we translate the numbers into words. That degree of smoothness is so remarkable that it demands explanation. To understand why this matters, we must think in the language of gravitational entropy. Ordinary entropy, the entropy of heat and molecular motion, works according to familiar intuition. A uniform distribution of gas seems simple, and a scattered distribution seems messy. But gravity prefers the opposite. Under gravity, structure is disorder. Clumps, clusters, dense pockets of matter, and the eventual formation of black holes represent the high entropy states. Smoothness is the rarest arrangement, the most delicate, the least likely. A smooth universe is one that has not yet explored its full gravitational possibilities. Imagine the cosmos as a vast plain. On this plain lie countless ways to distribute matter. Most distributions are chaotic. Some form swirling densities. Others form massive compact systems. But the early universe was almost perfectly smooth, like a plain with no hills or valleys. No fluctuations in density larger than a tiny fraction of a fraction. Such a configuration is not something that gravity creates on its own. It is something gravity destroys. Over time, tiny irregularities grow, structures form, and gravitational entropy rises. But at the beginning, before gravity had time to do its work, the cosmos was arranged in the most special way imaginable. This smooth state is the reason entropy had room to increase. It is the reason the universe developed stars, galaxies, and black holes. It is the reason temperature differences formed, the reason chemistry unfolded, the reason life could emerge, and the reason each irreversible process around us feels like it is traveling down a slope in only one direction. If the cosmos had begun in a chaotic gravitational state, entropy would have already been high. No arrow of time would exist. No unfolding of structure would occur. The universe would be static in behavior, even as it expanded or contracted. Everything we identify as change would be washed away. This realization transforms the Big Bang from a mere beginning into a profound explanation for the direction of time. The universe did not emerge from randomness. It emerged from a state that was stupendously specific. The precision of the early smoothness cannot be overstated. If the distribution of matter had been slightly less uniform, gravity would have collapsed parts of the cosmos too quickly, preventing the growth of galaxies as we know them. If it had been slightly more uniform, structure would have taken billions upon billions of extra years to form, leaving the cosmos filled with diffuse radiation and little else. The universe did not just begin. It began with conditions tuned in a way that allowed complexity to blossom. Yet even as these conditions shaped the entire future of cosmic evolution, they did not come with an instruction saying that time must flow from past to future. The laws of physics did not attach a sign pointing forward. Instead, the low entropy beginning created a slope in the landscape of possibilities. Once that slope existed, everything followed. Matter clumped, stars ignited, galaxies spiraled, black holes grew, biological life unfolded, conscious minds appeared. Every process climbed the slope of increasing gravitational entropy. The arrow of time is simply the shadow cast by that rise. To see how extraordinary this initial state was, consider what happens when gravity is allowed to run its course. Massive objects clump, dense regions collapse, black holes form. A single black hole contains an entropy so enormous that it dwarfs the entropy of all the matter that fell into it. A black hole with the mass of a single star has an entropy far exceeding that of the gas clouds from which it formed. A supermassive black hole found in the center of a galaxy, with the mass of millions or even billions of stars, contains a gravitational entropy almost beyond imagining. In the early universe, none of these existed. The absence of structure meant gravitational entropy was minuscule compared to what it could become. This gives us a window into the past. When we look at the early universe, we are seeing a cosmos sitting at the bottom of an enormous entropy well. As the universe expands and structures grow, entropy climbs higher and higher. The direction we call future is simply the direction in which entropy increases. The direction we call past is the direction in which entropy decreases. Because the universe began in such a low entropy condition, the entire history of cosmic evolution has unfolded as a one-way march toward higher entropy. This perspective might seem abstract, but it is intimately connected to the world we perceive. Every irreversible event in daily life, from the melting of ice to the spreading of perfume in a room, is tied to this cosmic beginning. The thermodynamic arrow of time in your kitchen exists because of the gravitational arrow of time in the universe as a whole. The two are not separate. They are the same arrow seen at different scales. The warmth leaving your coffee cup is part of a process that traces its roots back to the near-perfect uniformity of the early cosmos. And yet, the striking smoothness of the early universe remains an open question. Why was the cosmos born in such an improbable state? Why did it not begin in the chaotic configuration that gravitational statistics would consider typical? Inflation theory offers one possible explanation by suggesting that space underwent a tremendous expansion in the earliest moments, stretching out irregularities and leaving behind a smooth environment. But even if inflation occurred, we must ask why those inflationary conditions existed in the first place. Every answer seems to reveal a deeper question waiting beneath it. In this way, the Big Bang is not only an event, it is a puzzle whose pieces connect the laws of physics, the nature of time, the structure of space, and the very existence of consciousness. The early universe set the stage for all that would follow. Its smoothness encoded the direction in which processes would unfold. And from that direction, the arrow of time emerged, steady and unwavering. The early universe was not simply a compressed cloud of matter and radiation. It was an exquisitely tuned beginning, a starting point that left behind fingerprints still visible in the faint microwave glow that washes across the sky. That glow, the ancient remnant of the earliest light able to travel freely through space, carries the signature of a cosmos so uniform and so balanced that it challenges every expectation drawn from probability. Its nearly constant temperature, varying only by tiny fractions across the entire sky, speaks of an origin where gravitational disorder was almost non-existent. This smoothness allowed the cosmos to unfold like a story rising from quiet simplicity into grand complexity. To understand why smoothness matters, we must turn to the behavior of gravity. Gravity does not behave like the familiar forces we see in ordinary thermodynamics. When we heat a gas, its molecules explore more configurations and entropy rises. When we cool a gas, its molecules explore fewer configurations and entropy falls. But gravity reverses this intuition. A uniform distribution of matter is fragile and highly ordered. When gravity begins to act on small fluctuations, it pulls matter inward, forming clumps. Those clumps grow into clouds, and clouds collapse into stars. A star collapsing under gravity does not represent a decrease in disorder. It represents a profound increase. Within a collapsing cloud of gas, the possible arrangements of particles multiply beyond measure. The deeper the collapse, the greater the gravitational entropy. This is why black holes represent the highest entropy objects known in the universe. A black hole of stellar mass contains more entropy than entire galaxies' worth of gas. A supermassive black hole at the center of a galaxy contains more entropy than all the stars and planets in the galactic disk combined. This staggering imbalance in entropy tells us something powerful about the early universe. None of these structures existed at the beginning. There were no clusters, no galaxies, no black holes. The cosmos was smooth to a degree that prevented the gravitational collapse required for high entropy states. This smoothness placed the universe at the lowest end of its gravitational entropy spectrum. The existence of an arrow of time depends on this extraordinary beginning. As the universe expanded, tiny fluctuations in density began to grow. Regions slightly denser than average collected matter faster. Regions slightly less dense shed matter as gravity moved material toward the stronger gravitational wells. These early fluctuations were the seeds of everything to come. Without them, the universe would have remained smooth indefinitely. No galaxies would have formed, no stars would have ignited, no planets would have taken shape. Entropy would not have risen. Time would not have had direction. The universe expansion played an essential role in all of this. Expansion cools the cosmos and gives gravitational fluctuations room to grow. In a static universe, matter would not spread out in the same way. Heat would not dissipate. The cosmic environment would remain too hot for neutral atoms to form. The early conditions would freeze in place. But in an expanding universe, the distribution of particles becomes more diffuse. Temperature falls. Structures begin to emerge. And once structure formation begins, the irreversible rise of entropy becomes unstoppable. This rise in entropy is not restricted to gravitational collapse. It affects every process in the universe. As stars burn hydrogen into helium, they release energy into surrounding space. As that energy spreads, entropy rises. As atoms form from free electrons and protons, they radiate light, increasing entropy. As chemical reactions unfold, entropy rises. Even the formation of life on a planet increases entropy. Living systems maintain internal order only by exporting disorder into their surroundings. Every heartbeat, every breath, every thought you have contributes to the grand increase of entropy across the cosmos. All of these processes are possible only because the universe began in such a low entropy state. This starting point is not a trivial detail. It is the foundation of every irreversible event that has occurred since. The early cosmos set the stage. Entropy rose from that foundation. Time took on direction. The universe does not force time to move from past to future. It simply evolves. The evolution happens to unfold in the direction of increasing entropy, because that direction is overwhelmingly more probable than the reverse. Still, the most striking question remains: why did the universe start in such an incredibly smooth condition? From a thermodynamic perspective, the early cosmos appears far from equilibrium. But from a gravitational perspective, it appears precisely arranged. If the matter in the early universe had been distributed even slightly less uniformly, the cosmos would have collapsed too quickly, forming black holes before stars could ignite. If it had been slightly more uniform, structure would have emerged too slowly. Galaxies might not have formed at all. The universe would have remained a thin, diffuse mist. This delicate balance has prompted many scientists to explore inflation as a possible explanation. Inflation proposes that the universe underwent an unimaginably rapid expansion in its earliest fraction of a moment. This expansion would stretch any irregularities to enormous scales, smoothing out the cosmos like a sheet of cloth pulled taut. Inflation offers an elegant mathematical framework that explains the observed uniformity of the cosmic microwave background and predicts the tiny fluctuations that eventually grew into galaxies. Yet even inflation raises new questions. What caused inflation to begin? What caused it to end? What set the initial conditions for inflation itself? The mystery deepens when we consider that the laws of physics do not demand smoothness. They allow a vast range of possible initial states. The smooth state appears to be one of the rarest. This rarity lies at the heart of the arrow of time. The fact that the universe began ordered means entropy could grow, and because entropy could grow, processes could unfold irreversibly. The asymmetry we experience every day, from the shattering of a glass to the aging of a star, reflects the astonishingly special conditions of the Big Bang. In this sense, the universe origin is not simply a starting moment. It is the root cause of temporal direction. Everything that feels irreversible draws its meaning from that moment. Everything that evolves, everything that changes, everything that moves through what we call time does so, because the early cosmos began in a state that allowed those changes to unfold in only one direction. As we follow the arrow of time from its earliest roots into the later stages of cosmic evolution, we encounter a remarkable truth. Gravity, the force that binds planets into orbits and holds stars together, also plays a central role in reinforcing the arrow of time. Gravity does not merely shape space, it amplifies direction. The early universe invites a final and essential question. If smoothness is so improbable, if low gravitational entropy is such a rare and delicate configuration, then how did the cosmos find itself in that state at all? Every attempt to answer this question leads to deeper layers of mystery. Inflation, symmetry breaking, quantum fluctuations, vacuum states. All of these ideas offer potential explanations, but each relies on assumptions that push the puzzle one step backward. At the heart of the problem lies an unsettling truth. The universe did not begin in a random condition. It began in a state that appears finely arranged to allow the unfolding of structure, complexity, and an arrow of time. To appreciate how strange this is, imagine a giant cosmic lottery with an unimaginable number of possible starting states. Most of those states would create universes that collapse immediately. Others would expand forever without forming stars. Some would never cool enough for atoms to form. A tiny fraction would create galaxies, but not life. A still smaller fraction would produce complexity, but without a robust arrow of time. And only the smallest sliver of all possibilities would produce a smooth beginning, with just the right balance of density and temperature, enabling entropy to rise for billions upon billions of years. We live in a universe that emerged from that sliver. This realization shows that the Big Bang was not a chaotic fireball. It was a precise initial condition, one that set the cosmic stage for every irreversible process that would follow. Time does not flow because the laws demand it. Time flows because the early universe created a slope, a direction along which entropy could climb. If the cosmos had begun differently, the arrow of time might not exist. In some universes, the future might look like the past. In others, the concept of direction might have no meaning at all. In our universe, direction emerged naturally from the way gravity interacts with smooth matter. Gravity does not tolerate uniformity. It transforms even the tiniest fluctuations into vast structures. Once those structures appear, they begin a cascade of irreversible processes. A cloud collapses, releasing heat into space. A star ignites, fusing lighter elements into heavier ones and radiating energy outward. A supernova explodes, scattering elements into the cosmic sea. A black hole forms, storing entropy on a scale unmatched by any object in the universe. Each stage increases gravitational entropy. Each stage strengthens the arrow of time. Consider the life of a single star. It begins as a diffuse cloud of gas drifting through space. Gravity pulls the cloud inward, causing it to heat as it contracts. Eventually, the core becomes hot and dense enough for nuclear fusion to ignite. The star shines for billions of years, releasing energy created by fusing hydrogen into helium. Over time, the star exhausts its most easily fused fuel. It swells, cools, and eventually sheds its outer layers. Its core collapses. Depending on its mass, the remnant becomes a white dwarf, a neutron star, or a black hole. The evolution of the star is a one-way journey because entropy rises at every stage. Fusion creates disorder. Expansion creates disorder. Collapse creates disorder. At no point does the process reverse. A star never unburns its fuel. It never recoalesces into its original gas cloud. The arrow is absolute. This same principle governs galaxies. A galaxy is not a stable, timeless disk. It is a dynamic structure constantly reshaped by gravitational interactions. Stars orbit the galactic center. Gas clouds collide. Supernovae blast material outward. Black holes swallow matter, growing heavier and storing more gravitational entropy. These processes cannot run backward. They are part of the great expansion of possibility that began when the universe was smooth. Even the large-scale structure of the universe reflects this rise. The filaments and voids that form the cosmic web are expressions of gravity, amplifying tiny ancient fluctuations. Over cosmic time, matter flows from voids into filaments, forming dense clusters connected by bridges of gas and galaxies. As this network grows, the number of microscopic configurations increases dramatically. Structure formation is one of the most powerful engines of entropy in existence, and it all traces back to the special conditions at the beginning. This perspective illuminates a surprising connection between gravitational physics and thermodynamics. The earliest cosmos had incredibly low gravitational entropy, yet very high thermal entropy. Its heat was intense, but its gravitational structure was minimal. These two forms of entropy are not competing, they are complementary. Thermal entropy governed the motion of particles in the hot early plasma. Gravitational entropy governed the potential for structure to form. When the universe expanded and cooled, thermal processes gave way to gravitational ones. The smooth plasma transitioned into a world where gravity could sculpt matter into ever more complex configurations. The interplay between these two types of entropy reveals why the Big Bang created a universe with direction. High thermal entropy by itself cannot create an arrow. Thermal equilibrium has no direction. But low gravitational entropy provides a path for irreversible structure formation. The balance of these entropies created the perfect conditions for time to acquire meaning. This alignment of initial conditions transformed the universe from a timeless geometric object into a dynamic evolution with a clear sense of before and after. Yet even as we describe these processes, the ultimate origin of the low entropy state remains elusive. Was the universe born from a quantum fluctuation in a pre-existing state? Was it the result of a deeper symmetry? Did inflation stretch irregularities into smoothness? Or does the answer lie in physics we have not yet discovered? At present, these questions remain open. What is clear is that the universe beginning acted as the seed from which the arrow of time grew. We can think of the Big Bang not as an explosion, but as the initial page of a cosmic manuscript. That first page contains information that shapes the entire story. Smoothness allowed entropy to rise. Rising entropy created direction. Direction allowed complexity. Complexity gave rise to stars, planets, chemistry, life, and consciousness. And consciousness gave rise to the experience of time flowing from past to future. In the next chapter, we turn to the force that turns smoothness into structure. The force that takes a calm early universe and sculpts it into galaxies, stars, and black holes. The force that amplifies the arrow of time and anchors it in the geometry of space-time. That force is gravity. Gravity is the quiet architect of the universe. It sculpts galaxies from chaos, ignites stars from cold clouds, and carves black holes from collapsing matter. Yet beyond shaping the visible cosmos, gravity plays a deeper and far more surprising role. It is one of the primary engines that drives the arrow of time. When the universe began in its smooth early state, gravity was nearly powerless. But as the cosmos expanded and cooled, gravity awoke. Once awake, it began converting the universe's pristine uniformity into a landscape rich with structure, motion, and irreversible change. Without gravity, the arrow of time would be faint and fragile. With gravity, it becomes bold and unmistakable. To understand how gravity creates direction, imagine a vast cloud of gas drifting in space. At first, the cloud is almost perfectly uniform, with only tiny differences in density. If the universe contained only one such cloud and no gravitational attraction, that cloud would remain spread out forever. Nothing would cause it to clump. No structure would form. Entropy would stay nearly constant, and time would lack any sense of irreversible flow. But gravity changes this. Even the smallest fluctuation in density becomes a seed. Regions slightly denser than their surroundings pull in more material. As they gain mass, their gravitational pull strengthens. They grow faster. Eventually, the cloud collapses inward. As it collapses, it heats. The heating is not a trivial detail. It is the signature of entropy rising. When matter collapses under gravity, potential energy converts into heat. That heat radiates outward into space, making the surroundings more disordered. The collapse itself represents a dramatic increase in gravitational entropy, because the number of microscopic arrangements for a dense cluster of matter is vastly greater than the number for a smooth distribution. A collapsing cloud has more freedom internally, more possible states, more ways its atoms can be arranged while still producing the same macroscopic shape. The universe takes this path because the path contains an extraordinarily large number of possibilities. The story becomes even richer when the collapsing cloud reaches a critical threshold. At the core, pressure and temperature climb until nuclear fusion ignites. When fusion begins, the object becomes a star. Fusion is an irreversible process that releases energy at an astonishing rate. That energy floods outward, spreading through space and increasing entropy on cosmic scales. A star is not only a radiant beacon in the night sky, it is a monumental engine that reinforces the arrow of time. It consumes order and emits disorder. It transforms hydrogen into helium and light into heat. It lights the universe with irreversible change. Stars live for long stretches measured in billions of years, but they are temporary. When a star exhausts its easy fuel, it expands, cools, and eventually sheds its outer layers. Its core collapses, depending on the star mass. The remnant becomes a white dwarf, a neutron star, or a black hole. This final collapse is a spectacular example of entropy rising. A neutron star packs more entropy into a sphere the size of a city than an entire cloud of gas held in its original form. A black hole increases entropy even more dramatically. The entropy contained in a single black hole can exceed the entropy of countless stars combined. The larger the black hole, the greater the gravitational entropy it stores. The early universe had none of these dense objects. As gravity sculpted matter into them, entropy grew, and the arrow of time strengthened. This dynamic is universal. It does not matter whether we look at a collapsing cloud, a forming galaxy, or the cosmic web stretching across billions of light years. In every case, gravity acts as an amplifier. It takes tiny fluctuations and turns them into immense structures. That amplification is inherently irreversible. Once a galaxy forms, it will not spontaneously return to a smooth distribution. Once a star is born, it will not unignite. Once a black hole forms, it will not release its concentrated matter back into a uniform cloud. Gravity ensures that the universe moves away from its initial smoothness toward a future filled with complexity and disorder. Even the large-scale structure of the universe reflects gravity power to build the arrow of time. The cosmic web, made of filaments, clusters, and vast voids, is a map of how entropy has grown over billions of years. Matter flows along these filaments toward deeper wells, creating clusters of galaxies that contain unimaginable numbers of stars. These clusters collide, merge, and evolve. Their central black holes absorb matter and grow even larger. Each step increases entropy. Each step reinforces direction. In this way, gravity is not merely a force, it is a cosmic organizer. It takes the low entropy conditions of the early universe and guides them toward higher entropy states. It does not violate the fundamental symmetries of physics. The laws remain reversible at the microscopic level. But gravitational interactions among countless particles create patterns so improbable to reverse that reversal becomes practically impossible. The arrow of time emerges not from the laws themselves, but from the statistical consequences of gravity applied to smooth initial conditions. The smoothness of the early universe was a beginning. Gravity was the sculptor. Entropy was the measure. Time was the direction that emerged from their collaboration. The expansion of the universe provided the stage. The cooling of matter provided the materials. Gravity provided the movement. Together, these ingredients shaped the history of cosmic evolution. As we follow this story deeper into the heart of gravitational physics, we discover that the most extreme objects in the universe carry the strongest imprint of the arrow of time. These objects, the gravitational giants known as black holes, are not only astrophysical phenomena. They are reservoirs of entropy so vast that they dominate the cosmic ledger. To understand time direction fully, we must confront the behemoths that anchor the universe thermodynamically. Black holes are the deepest shadows cast by gravity. They are regions where matter collapses so completely that not even light can escape. Yet despite their darkness, they are among the brightest milestones in the story of cosmic entropy. A black hole does not merely store mass. It stores information in a way that gives it an entropy far greater than any ordinary object of equal size. This extraordinary capacity makes black holes the ultimate engines of irreversibility. They pull the universe forward along its arrow of time, ensuring that the cosmos never returns to its early smooth state. To understand why black holes carry such enormous entropy, imagine compressing a star into a smaller and smaller volume. As matter becomes dense, the number of possible microscopic configurations grows. The atoms rearrange, the particles shift. The gravitational field becomes more intense. With each step, entropy rises. When the collapse becomes unstoppable, the star passes a point of no return. A surface forms around it, a boundary from which nothing can escape. This boundary is called the event horizon, and the area of this horizon is directly related to the amount of entropy contained within the black hole. The larger the area, the greater the entropy. Even a black hole formed from a single star contains an extraordinary amount of entropy. A supermassive black hole found at the center of a galaxy contains a staggering amount more. This immense entropy reveals something profound about the arrow of time. The early universe contained almost no black holes. Its gravitational entropy was extremely low. As time passed, gravity sculpted matter into stars and galaxies. Stars collapsed, mergers occurred, black holes formed and grew. Each step increased the entropy of the universe far beyond what ordinary thermal processes could achieve. Black holes are the universe's most extreme expressions of the tendency toward disorder. They are the endpoints of gravitational evolution, the deepest wells where the arrow of time becomes unavoidable. Yet black holes do more than store entropy, they radiate it. Stephen Hawking discovered that black holes are not perfectly dark. They emit a faint glow that we now call Hawking radiation. This radiation arises from quantum effects near the event horizon, where pairs of particles and antiparticles can form. One particle escapes while the other is absorbed. The escaping particle carries energy away from the black hole, making it lose mass over time. This evaporation process is incredibly slow for large black holes, unfolding over timescales far beyond human comprehension. But it establishes a remarkable truth. Even black holes, the universe's most gravitationally extreme objects, participate in the irreversible rise of entropy. This radiation is not just a curiosity. It demonstrates that the arrow of time persists even at the very edge of space-time physics. The process cannot be reversed. A black hole that evaporates cannot spontaneously regather its radiation and restore itself to its earlier form. The growth of entropy is encoded into the very mathematics describing black hole behavior. In this way, black holes anchor the arrow of time at the intersection of gravity and quantum theory. They show that irreversibility is not limited to familiar thermodynamic systems. It reaches into the deepest regions of space-time. Black holes also play a central role in shaping the large-scale evolution of galaxies. Many galaxies, including our own, contain supermassive black holes at their centers. These black holes grow by absorbing gas, stars, and sometimes smaller black holes. When they merge, the combined black hole carries even more entropy than the sum of the two. This additive effect reinforces a pattern seen across cosmic history. No matter how matter rearranges, no matter how galaxies collide or stars evolve, the overall entropy increases. Black holes ensure that this increase is not subtle, it is enormous. The arrow of time becomes even clearer when we observe the behavior of matter falling into a black hole. As matter approaches the event horizon, it stretches and heats. Energy radiates outward. The environment becomes turbulent and chaotic. All of this increases entropy before the matter ever reaches the horizon. Once it crosses the boundary, its information becomes inaccessible to the rest of the universe. The loss of accessibility further increases entropy because many different initial configurations can produce the same final black hole. This blending of possibilities strengthens the time direction even more. Gravity takes the smooth early universe and sculpts it into a cosmos filled with structures that cannot be undone. Once galaxies form, they do not unform. Once stars burn their fuel, they do not unburn it. Once black holes appear, they do not release their contents back into their original states. The irreversible growth of gravitational entropy means that time moves away from the Big Bang and never returns. The future is the direction in which black holes grow. The past is the direction in which they do not yet exist. The more we study gravity, the clearer this picture becomes. Gravity converts uniformity into complexity. It turns simplicity into structure. It transforms smoothness into a universe filled with motion, radiation, and irreversible evolution. Without gravity, entropy would still increase, but its rise would be slow and limited. With gravity, the rise becomes immense and unstoppable. Gravity is not merely a force. It is the great amplifier of the arrow of time. As we continue our exploration, we discover that irreversibility does not come solely from the macroscopic behavior of stars and galaxies. It also emerges from the microscopic behavior of quantum systems. Even though the fundamental equations of quantum mechanics appear time-symmetric, the process of measurement and entanglement creates a form of asymmetry that mirrors the thermodynamic arrow. To fully understand why time flows forward, we must journey into the strange and subtle world where quantum theory meets irreversibility. Gravity is often imagined as a simple attraction between masses, a pull that shapes orbits and holds objects in place. But the true nature of gravity is far richer. It is not merely a force acting across space. It is the curvature of space itself, responding to energy and mass. When we describe a planet orbiting a star, we are really describing a path carved into the fabric of space-time. When we describe a star collapsing into a black hole, we are describing a region of space-time folding so deeply that escape becomes impossible. Gravity is geometry in motion, and that geometry provides the universe with the deep framework upon which the arrow of time unfolds. This geometric nature of gravity also reveals why the early universe smoothness was so significant. In a perfectly uniform cosmos, the curvature of space-time is simple. It does not twist or bend sharply. It does not create deep wells that trap light or matter. A smooth universe is a gentle universe, one in which entropy is almost entirely thermal rather than gravitational. But the moment small fluctuations begin to grow, the curvature of space-time becomes more intricate. Valleys deepen, peaks rise. Matter falls toward these valleys and gathers. As matter gathers, the space-time around it curves further, creating a feedback loop that accelerates structure formation. This feedback loop ensures that once the early universe begins to deviate from perfect smoothness, the process becomes irreversible. Irreversibility lies at the heart of the arrow of time. Once a cloud collapses into a star, the space-time curvature around it becomes radically different from the curvature around the original cloud. The process cannot simply reverse itself. The heat released during collapse has already escaped into the wider universe, increasing entropy in a way that cannot be undone. The outward radiation carries information that cannot be retrieved. The star that forms is a new state with more disorder hidden within its structure, and the space-time around it reflects that transformation. When entire galaxies take shape, the same logic applies on grander scales. The gravitational potential wells created by galactic structures are deep and distinct. Restoring the early uniformity would require not only reversing the motions of uncountable stars, but also reversing the curvature of space-time itself. The probability of such a reversal is unimaginably small. It is so small that for all practical purposes, it is zero. This is why the arrow of time is not simply a feature of matter. It is a feature of the geometry of the universe. Once structure begins to form, space-time becomes increasingly complex, and that complexity cannot unravel itself. Black holes represent the ultimate expression of this irreversible curvature. A black hole is a region where space-time has curved to such an extreme degree that all paths lead inward. The event horizon is not a physical surface, but a geometric boundary. Inside that boundary, the direction of space-time funnels matter toward the center. Even if the laws of physics allow processes to run backward in principle, the geometry of a black hole makes reversal impossible in practice. To reverse the formation of a black hole, every particle of radiation it emitted, every wave of heat released during collapse, every tremor of space-time would need to return exactly to its source. The chance of such a feat is essentially non-existent. This is why black holes dominate the entropy ledger of the universe. They are more than objects. They are monuments to irreversibility. Each black hole marks a colossal leap in gravitational entropy that ensures time moves in one direction and never cycles back. The early universe had almost no gravitational curvature. The future universe will be shaped mainly by the geometry created by black holes. The difference between these two states is the measure of the arrow of time. Even the slow decay of black holes through Hawking radiation deepens this direction. The evaporation process spreads energy outward in a way that cannot be undone. The emitted radiation carries entropy with it, gradually transforming the black hole into heat distributed across the sky. This process unfolds over timescales measured in numbers so large they defy normal comprehension. Yet the direction is clear. A black hole forms. It grows. It radiates. It fades. Nowhere in these stages is there a turn backward. Gravity, therefore, provides the cosmic scaffolding that supports the arrow of time. In the early universe, gravity was quiet, because smoothness left it little to sculpt. As the cosmos expanded and cooled, gravity became active. It built structure. It deepened curvature. It produced stars, galaxies, and black holes. Each of these creations increased entropy in ways that can never be reversed. The direction of time emerges from this growth of gravitational complexity. Yet even with this clarity, a deeper puzzle remains. Gravity explains the arrow of time on cosmic scales, but what about the microscopic scales governed by quantum mechanics? The equations of quantum theory, like the equations of classical mechanics, are time-symmetric. They do not distinguish past from future. They evolve wave patterns with perfect mathematical reversibility. And yet, when we observe or measure a quantum system, the result seems to choose a direction. Something in the process of measurement appears to introduce irreversibility. To understand why time flows forward at the quantum level, as well as the cosmic level, we must leave the realm of stars and galaxies and step into the strange landscape of quantum states, superpositions, and entanglement. There, in the quiet world beneath the level of atoms, lies another thread that weaves into the arrow of time. Quantum mechanics reveals a universe built from possibilities rather than certainties. At its deepest level, reality behaves like a shifting landscape of waves, each wave representing a range of potential outcomes. A particle is not located in one precise place until it is observed. Instead, it exists in a superposition, a blend of all the positions it could occupy. The equation that governs this evolution, the Schrödinger equation, treats time as a coordinate and moves it forward or backward with perfect indifference. If we were to know a quantum state with infinite precision, we could evolve it toward the future or the past without encountering any barrier. The mathematics would work perfectly in both directions. But the world we observe is not built from perfect isolation. It is built from interactions. And once interactions join the picture, the arrow of time begins to emerge in a subtle but powerful way. Imagine holding a single electron inside a perfectly shielded laboratory, a place where stray vibrations, drifting photons, and passing fields cannot disturb it. In such an ideal environment, the electron would behave like a quiet ripple in space, spreading out in a wave that evolves cleanly in either direction along the time coordinate. But no such perfect isolation exists in nature. Every particle interacts with something. Each interaction entangles the particle with part of the environment. Entanglement is not a metaphysical connection. It is a physical accounting of shared information between systems. As soon as an electron becomes entangled with a photon, or an atom, or even the faint quantum vibrations of space itself, its state ceases to belong to it alone. The once pure wave pattern becomes woven into a far larger tapestry. This weaving of information across many degrees of freedom is what physicists call decoherence. Decoherence does not destroy possibilities. It distributes them so widely that they can no longer be recombined. If the universe were small and simple, we could in principle reverse every interaction, capture every photon, and reconstruct the original state. But the actual universe is enormous and complex. Interactions produce entanglement that spreads outward like the ripples from a stone dropped into a still lake, except the lake here has no edges and no limit to its size. Reversing this spread would require manipulated coordination across an uncountable number of particles. The probability of doing so is so small that it is effectively zero. Decoherence therefore creates a practical arrow of time rising from the quantum realm, even though the fundamental equations remain mirror-symmetric. This helps explain why quantum measurement feels one-directional. Before a measurement, a particle exists in overlapping possibilities. After a measurement, only one outcome remains. The act of observing does not involve a conscious mind stepping in. It is simply the process of correlating the system with something larger. A measurement device becomes part of the entangled structure. The combined system, made from particle and apparatus and environment, evolves in a way that cannot be unentangled without reversing every microscopic interaction that occurred. The collapse we speak of is not a literal physical collapse. It is the narrowing of accessible possibilities once entanglement has locked the system into one recorded outcome. Entropy in the quantum world is tied directly to the growth of entanglement. A quantum system that begins in a simple state with little entanglement will gradually become more intertwined with the environment as time progresses. These correlations hold information about the system history. The more entanglement that forms, the harder it becomes to isolate the system or reverse its evolution. Moving backward through time would require unweaving these correlations one by one. But the number of correlations grows so quickly and spreads through so many particles that undoing them becomes beyond any reasonable reach. The growth of entanglement therefore mirrors the rise of entropy in thermodynamics. Both processes begin with simplicity and end with complexity. Both reveal the same asymmetry between past and future. Even the famous thought experiments of quantum mechanics point toward this directionality. Consider Schrödinger cat, not as a metaphor, but as a description of how macroscopic objects become entangled with microscopic states. The cat becomes correlated with the outcome of a quantum process. Once that correlation is established, reversing the event would require disentangling not only the cat, but every atom in the air around it, every photon that bounced off its fur, every vibration that traveled through the floor, and every microscopic influence that propagated outward. The chain of entanglement forms a branching structure of possibilities that spread through the environment. These branches never recombine in practice. They grow forward, not backward. They form a temporal tree whose roots lie in the past and whose branches extend into the future. This forward growth can be seen even in simple quantum systems. A photon traveling through a partially reflective surface may take one path or the other according to its wave pattern. But once the photon interacts with anything that records the path, even a dust particle or a faint atom, the two branches can no longer interfere. The environment has stored the information about the path, and that storage creates irreversibility. To reverse the process, one would need to restore the environment to the precise microscopic state it had before the photon interacted with it. Doing so is practically impossible. Once again, entanglement turns symmetry into direction. Thermodynamic entropy and quantum entanglement therefore describe the same story from different perspectives. One speaks of the number of microscopic configurations compatible with a macroscopic state. The other speaks of the number of correlations embedded in a system history. Both rise over time. Both are irreversible in practice, and both connect directly to the structure of the early universe. The cosmos began in a state of low entropy and low entanglement. As time progressed, interactions wove complexity into matter and energy. Structures formed, information spread, entropy grew, entanglement increased. The arrow of time emerged from this gradual deepening of correlations. The remarkable insight hidden in quantum mechanics is that the laws themselves do not force this direction. The equations are unbiased. They allow evolution toward the future or the past without preference. The direction arises from the initial conditions. A universe beginning in a simple, low entropy and low entanglement state will develop into one with greater complexity. Entanglement spreads, decoherence grows, measurements record outcomes that cannot be undone. The universe appears to move forward because forward is the direction in which complexity increases. Quantum mechanics therefore reinforces the arrow of time rather than challenging it. At its heart lies a symmetry. But when that symmetry interacts with the real environment, with heat and light and atomic collisions and cosmic radiation, the symmetry gives birth to direction. The arrow of time becomes the natural result of a universe that started in a simple state and evolved into a complex one. Past and future are not written in the equations. They are written in the unfolding of complexity itself. Modern physics contains few principles as deep and as astonishing as CPT symmetry. This symmetry tells us that if we flip charge, flip spatial orientation, and reverse the direction of time, the laws governing every known particle remain exactly the same. Nothing breaks, nothing changes, nothing becomes inconsistent. A particle moving forward in time is equivalent, in this mirrored description, to an antiparticle moving backward in time. A left-handed interaction becomes a right-handed interaction. Matter transforms into antimatter, but the equations continue effortlessly. It is as if the universe contains a hidden reflection, a grand mirror that, when applied perfectly, leaves the entire mathematical structure untouched. This symmetry does not come from philosophical speculation. It arises naturally from the structure of quantum field theory, the framework that describes the behavior of particles, forces, and interactions. In this framework, the laws treat time as a coordinate and not as a flowing entity. They do not embed a preferred direction. They simply describe how fields evolve when probed at the tiniest scales. When physicists apply all three operations together, charge flip, parity flip, and time reversal, the mathematics yields a world that is fully consistent, as real and coherent as the world we inhabit. This alone reveals something profound. If time had a built-in direction carved into the laws themselves, CPT symmetry would fail. But it does not fail. It stands firm, verified by every experiment performed so far. Yet the world we experience does not look like a perfect CPT reflection. The universe we see contains far more matter than antimatter. Stars, planets, people, and everything we call familiar are built from matter. Antimatter exists, but it is rare, created in small amounts through high-energy processes and destroyed quickly when it encounters ordinary matter. If the laws are symmetric under CPT, why does the cosmos not contain equal amounts of both? Why does time seem to push forward rather than backward if the fundamental equations care so little about direction? To answer this, we must examine CP violation, a subtle imbalance observed in certain particle interactions. CP refers to the combination of charge flip and spatial flip. In a perfectly symmetric world, flipping both should leave the interaction unchanged. But experiments have shown that certain decays involving particles called kaons and b-mesons behave slightly differently under CP operations. These differences are tiny, but they are real. They hint that the universe's early evolution may have favored matter over antimatter. But even these differences do not break CPT symmetry. When time reversal is included along with CP, the symmetry is restored. This means the fundamental laws remain fully balanced. The asymmetry we observe must therefore come from initial conditions rather than the laws themselves. The arrow of time plays directly into this understanding. The laws do not insist on a forward flow of events. They permit evolution backward just as easily as forward. But the universe does not begin in a state that is symmetric between past and future. It begins in a state of extremely low entropy. This low entropy condition provides a slope along which processes unfold. The future becomes the direction toward greater entropy, greater possibility, and greater complexity. The past becomes the direction toward lower entropy. The laws do not prefer either direction. The initial conditions do. To see how strange this is, imagine watching a video of a particle collision. If the video were played backward, the fundamental equations would still describe the reversed motion perfectly. Nothing in the mathematics would mark the reversed version as forbidden. But if you watched a video of a glass shattering or a cloud collapsing into a star, the backward version would look unnatural, because the world we inhabit is filled with macroscopic processes whose outcomes have been shaped by rising entropy. These processes are not forbidden by the laws, they are forbidden by probability. CPT symmetry remains true, but the universe adds its own asymmetry by beginning in a special state. The concept of a particle moving backward in time might sound like science fiction, but within the mathematics of quantum field theory, it is simply another way of describing an antiparticle. This reinterpretation is not a metaphor. It is an exact equivalence. When we look at a Feynman diagram, the visual tool physicists use to track interactions, an antiparticle can be drawn as a particle traveling backward along the time coordinate. This representation highlights how deeply time symmetry is woven into the theory. The mathematics does not care whether the evolution points forward or backward. The diagram works either way. Yet this time, symmetry at the microscopic level does not erase the arrow of time at the macroscopic level. Measurement, decoherence, and entropy growth ensure that once information spreads outward, once a record forms, once correlations deepen, the system cannot return to its earlier state. The laws allow reversal, but the universe does not give us the conditions needed to perform it. Time reversal requires an environment as finely tuned as the earliest moments after the Big Bang. But the actual environment becomes increasingly entangled, disordered, and complex as time progresses. Macroscopic reversals become so improbable that they never happen. CPT symmetry therefore highlights a remarkable truth. The arrow of time is not embedded in the laws, it is embedded in the universe history. The early cosmos determined the direction. CPT symmetry shows what the world would look like if the direction were reversed, and if every particle were replaced by its opposite, and if every spatial orientation were flipped. Under these transformations, the laws would still hold. The reversed world would be just as valid as ours. But we do not live in that reversed world. We live in the world that grew from a smooth, low entropy origin, a world where complexity rises as time moves forward. This realization shifts the mystery of time from the laws to the beginning. The question is not why the laws choose a temporal direction. They do not choose at all. The question is why the universe began in a state that allows entropy to increase. Why did the cosmic history unfold along the path that reveals only one side of the symmetric equations? Why did we inherit an arrow instead of a balance? These questions point directly to cosmology. The expansion of the universe, the rise of structure, the growth of gravitational entropy, and the cooling of radiation all emerge from the initial state. To understand the arrow of time fully, we must investigate how cosmic expansion shapes the direction we experience. The next step is to explore why an expanding universe supports the arrow of time while a contracting one might reverse or erase it. Expansion does more than stretch space. It stretches the very possibilities that entropy may grow into. When we turn to the large-scale motion of the cosmos, we find that the arrow of time is not an isolated feature of quantum mechanics or thermodynamics. It is built into the evolution of space itself. The universe is not static, it stretches. Every distant galaxy drifts away from every other, not because they are flying through space, but because space itself grows between them. This expansion is one of the most important discoveries in modern cosmology, and it carries profound implications for the arrow of time. Without cosmic expansion, the universe as we know it would not cool, would not form structure, would not allow entropy to climb, and would not provide the conditions in which time acquires direction. Expansion is not the cause of the arrow, but it is the stage that allows the arrow to express itself clearly and unmistakably. In the earliest moments after the Big Bang, the universe was hot, dense, and filled with energy moving in all directions. But even in this early plasma, expansion was already at work. As space grew, matter became more diffuse. The temperature dropped. Particles that once collided endlessly found more room to move. When the temperature fell enough, protons and electrons joined to form neutral atoms. When the temperature fell further, the first hints of structure began to appear. None of this would have been possible without expansion. A static universe would remain hot and dense. Atoms would not form. Stars would not ignite. Galaxies would not grow. Entropy would remain trapped within a narrow range of possibilities. The arrow of time would be weak, or perhaps non-existent. Expansion therefore acts as the cosmic engineer that gives entropy room to rise. When matter spreads out, it can fall into deeper gravitational wells. When energy thins, it can radiate more freely. When temperature drops, new states of matter become possible. Each of these events produces irreversible consequences. Once atoms form, they do not unform without enormous energy. Once stars ignite, they do not unignite. Once galaxies assemble, they do not unwind back into a smooth fog. Expansion stretches the canvas of the universe so that gravity, thermodynamics, and quantum processes can paint a story filled with direction. Consider what would happen if the universe were not expanding but static. Without expansion, radiation would remain extremely energetic. Every region would be thick with collisions. The universe would hover in a kind of perpetual equilibrium. Entropy would be unable to make large gains because the system would remain dense and uniform. Complexity would struggle to arise because the intense environment would wipe out delicate structures. Time might still exist as a coordinate, but the arrow that accompanies irreversible processes would be weak or even absent. A static universe is a universe where direction loses meaning. In contrast, our universe grows larger every moment. As galaxies drift apart, the density of matter decreases. Lower density allows gravitational fluctuations to grow. Regions with slightly higher density gather matter and eventually collapse into stars. Regions with slightly lower density become cosmic voids. The cosmic web forms an intricate network of filaments and clusters separated by vast expanses of emptiness. This structure is a physical signature of entropy rising over time. It could not have emerged in a universe that stayed the same size. Expansion opens the door to the irreversible deepening of gravitational entropy. The cooling driven by expansion is equally important. In the early universe, temperatures were so high that no atoms could form. Protons and electrons moved too rapidly to bind. Only after expansion cooled space to a few thousand degrees, Kelvin could neutral atoms assemble. And only after further cooling could molecules form. Once molecules existed, chemistry could unfold. Once chemistry unfolded, planets could take shape. Once planets formed, environments suitable for life could emerge. Every one of these transitions increased entropy. Every one was irreversible. None would have occurred without cooling, and cooling is a direct consequence of expansion. Even the faint glow of the cosmic microwave background owes its existence to expansion. When this ancient radiation was released, the universe temperature was around a few thousand degrees Kelvin. Today, after billions of years of expansion, it has cooled to only a few degrees Kelvin above absolute zero. This vast decrease in temperature reflects the stretching of space itself. The wavelengths of the early radiation have been stretched to nearly 1,000 times their original size. This stretching is irreversible. There is no natural mechanism to compress those wavelengths back to their original lengths. The cooling of the cosmic background is a clear imprint of the arrow of time written across the entire sky. Expansion also prevents the universe from collapsing back into a uniform state. If gravity alone were at work and expansion were absent, matter would clump so aggressively that the entire universe might collapse into a single enormous black hole. In such a universe, entropy would rise quickly and then stop, trapped in a gravitational prison. Time would exist, but the arrow would be short-lived because the process of entropy increasing would reach its ceiling early. Instead, expansion counteracts gravity on large scales. It allows galaxies to remain separated rather than merging into one giant structure. This balance ensures that the universe can continue evolving for billions of years. Entropy continues rising gradually, rather than reaching a sudden maximum. The arrow stretches across cosmic history instead of ending abruptly. The fate of the universe is also tied to expansion. If expansion continues indefinitely, matter will grow increasingly thin. Stars will exhaust their fuel. Black holes will swallow what they can and eventually evaporate through faint radiation. Over unimaginably long timescales, the universe may approach a state sometimes called heat death. In this future, entropy is so high and matter so diffuse that no new structures can form. No new stars can ignite. No biological processes can unfold. Time still exists as a coordinate, but the arrow becomes silent because there are no available pathways to increase entropy further. In this distant era, the universe reaches statistical equilibrium. The direction we experience today fades into cosmic quiet. Some theories once imagined the possibility that expansion might reverse. In such a scenario, the universe would reach a maximum size and then begin to contract. During contraction, temperatures would rise. Radiation would grow more energetic. Matter would move closer together. A great cosmic collapse would eventually mirror, in some respects, the early universe. But would the arrow of time reverse? Would entropy decrease? Would broken structures reassemble, stars unburn, and matter regain its smoothness? Physics gives a clear answer. Even if contraction occurred, the arrow would not reverse. Rising entropy is tied to probability, not to the direction in which the scale of the universe changes. Contraction would not magically undo the thermodynamic history written across cosmic time. Instead, entropy would likely continue rising until the final moments. The universe would fall inward, carrying the full weight of its irreversible past. Modern observations show that the universe is not contracting and shows no sign of doing so. In fact, expansion is accelerating. A mysterious form of energy, often called dark energy, pushes galaxies apart at an increasing rate. This acceleration ensures that expansion will not reverse. Instead, it will continue indefinitely. This means the arrow of time, supported by expansion, will persist as long as there are processes capable of increasing entropy. As stars fade and black holes evaporate, the opportunities for entropy increase will shrink, and the arrow will eventually weaken, but it will not reverse. Expansion, therefore, plays a unique role in the story of temporal direction. It does not create the arrow by itself. Instead, it enables the universe to evolve in a way that makes the arrow manifest across every scale. Without expansion, entropy could not rise as dramatically. Gravity could not sculpt structure. Radiation could not cool. Life could not emerge. Memory could not form. Conscious beings could not experience a difference between past and future. Expansion is the cosmic frame that allows direction to appear. The universe does not force time to flow, but expansion gives time the space in which its arrow may unfold. To understand this arrow fully, we now ask a new question. If the laws are symmetric and the universe reveals only one direction, could there exist another cosmos where the arrow points the opposite way? Could time, in some deeper sense, be two-sided? The universe we inhabit moves in a single direction. Entropy rises, structure becomes more complex. Records accumulate, stars burn through their fuel, black holes grow and radiate. Time flows from a low entropy past toward a higher entropy future. Yet the laws of physics do not choose this direction. They allow evolution toward either temporal side with equal mathematical elegance. This raises a profound question. If the fundamental equations are symmetric, why does only one temporal direction appear in our cosmos? And even more intriguing, could there exist another universe where the arrow of time points the opposite way? This possibility, once considered speculative, has gained renewed attention in recent decades as physicists examine the deep symmetry known as CPT. According to CPT symmetry, if we flip charge, flip spatial orientation, and flip time, the resulting world would obey the same laws as ours. This is not optional. It is required by the mathematics of quantum field theory. If this symmetry holds, and all evidence suggests that it does, then there is nothing inconsistent about a universe where time runs in the opposite direction relative to ours. Such a universe would not violate physical law. It would be a mirror solution to the same equations. The idea becomes even more compelling when we consider the beginning of our cosmos. The Big Bang was not simply a burst of energy. It was a moment of extreme smoothness, low entropy, and delicate uniformity. From that condition, entropy could rise only in one temporal direction. But what if that smoothness was not inherently one-sided? What if the Big Bang was a temporal midpoint rather than a beginning? In such a scenario, our universe would expand forward in time from that moment, while a mirror universe would expand in the opposite direction. Both would emerge from the same boundary, but each would evolve with its own arrow of time pointing away from the shared origin. In recent years, some physicists have proposed models where this idea is not only possible, but natural. One such approach imagines the entire cosmos as a CPT symmetric system. In this picture, the Big Bang is a kind of mirror plane. On one side lies our universe, expanding forward in time, filled with matter, and governed by the arrow we observe. On the other side lies a universe where time flows away in the opposite direction, and where antimatter plays the dominant role. This mirror universe would not be behind us in time. It would not follow our future or precede our past. Instead, it would occupy its own temporal direction, emerging from the same boundary, but unfolding in reverse relative to our own arrow. To visualize this, imagine a single moment of perfect smoothness. From this moment, two separate expansions occur, one leading to our cosmos, the other to its mirror counterpart. Both sides begin with low entropy. Both sides gain complexity as entropy rises. But from the perspective of each inhabitant, time always flows forward. From our viewpoint, the mirror universe seems to run backward. From theirs, we run backward. Each reality contains an arrow. Each arrow points to its own future. The symmetry is perfect. This does not mean that the mirror universe is a reversed version of our daily world. It would not contain backward falling rain or reversed speech or backward growing trees. It would simply have its own thermodynamic history. Its stars would ignite and burn. Its galaxies would take shape. Its matter would obey the same equations we know. But its temporal ordering would be the opposite of ours, measured relative to the shared boundary. The symmetry is not about events moving backward. It is about entropy increasing in opposite temporal directions from a common origin. Some versions of this idea propose that dark matter may even consist of particles belonging to this mirror sector. If this were true, dark matter would not be made from the particles we know. It would be composed of mirror particles, living on the other side of the temporal boundary. These particles would feel gravity, but not ordinary forces like electromagnetism. They would be invisible to us except through the way they bend space. While this idea remains speculative, it offers a fascinating connection between cosmic symmetry and observable structure. The notion of a mirror universe also invites reflection on the nature of time itself. We often imagine time as a single thread, stretching from a beginning into a future. But if the universe is fundamentally symmetric, time may instead resemble a sheet that extends in two directions from a central line. Past and future would not be absolute. They would be local to each branch. Our experience of time would be shaped not by the laws, but by our location on this sheet. We travel on one branch. The mirror universe travels on the other. Both branches obey the same laws. Both branches are natural outcomes of the initial conditions. The key idea underlying this picture is that the arrow of time is not universal. It is relational. It depends on where you stand in the larger structure. Just as two observers in relativity may disagree about which events happen simultaneously, two observers in a CPT symmetric cosmos may disagree about which direction is past and which is future. Each would experience time flowing forward. Each would build memories of one direction. Each would see entropy rising, but their arrows would be oriented in opposite directions in the larger frame. This mirror picture also reframes the question of why our universe contains far more matter than antimatter. Instead of asking why matter dominates here, we may ask whether antimatter dominates in the mirror universe. If the overall system is perfectly balanced, then one branch may contain mostly matter, while the other contains mostly antimatter. The symmetry remains intact across the whole. Our branch contains the matter from which stars and planets form. The mirror branch contains antimatter fulfilling an equivalent role. The imbalance in our branch is not a violation of symmetry, but a reflection of the deeper two-sided structure. This idea does not claim that the mirror universe is accessible to us. It does not exist in our past or our future. It does not interact through ordinary forces. It is not a parallel world drifting beside us. It is simply the opposite temporal branch of the same fundamental reality. If true, it would provide a natural explanation for why the universe did not choose a temporal direction in the sense of law. The universe never chooses. The laws remain symmetric. The initial conditions create two arrows, one on each side of the boundary. The mirror universe hypothesis does not rewrite physics. It enriches the story of why time flows. It shows that the arrow of time is not absolute, but emergent. It arises from smoothness, entropy, expansion, and the way the cosmos unfolds from its earliest state. Our arrow points one way. The mirror arrow points the other. Both are valid. Both are natural. Both exist within the same symmetric mathematical framework. The next step is to ask why consciousness perceives only one arrow, why memory forms in only one direction, why awareness seems anchored to a forward-flowing timeline. To answer these questions, we must turn inward to the physics of information, the structure of thought, and the thermodynamics of memory. Time becomes personal when it enters the mind. The universe may evolve according to thermodynamic gradients and cosmic expansion, but the flow of time is felt only because consciousness exists to experience it. Every moment you recall, every expectation you hold, every plan you imagine is shaped by the direction in which memory points. The arrow of time is not only a physical phenomenon, it is a psychological one, woven into the structure of information inside the brain. Without memory, you would not feel the past behind you or the future ahead. You would float in a single featureless present. To understand why time seems to move, we must understand why memory forms in only one temporal direction. Memory is not stored by placing information into neat labeled compartments. It is built from physical processes unfolding through the nervous system. When neurons fire together, they strengthen connections. When chemicals flow across synapses, they modify pathways. Every recollection you have is a pattern etched into matter. These patterns depend on energy, motion, and entropy. They require the irreversible rearrangement of molecules. The brain cannot create memory without increasing entropy. The act of remembering is an act of thermodynamic change. When you learn something new, your brain takes a state with fewer possible microscopic configurations and transforms it into a state with many more. This increase in entropy anchors memory to a single direction. You remember the past because that is the direction in which entropy was lower. You do not remember the future because that direction contains more possible states and therefore cannot be encoded in a single stable pattern. Information theory gives a deeper explanation. Storing information requires taking a system with uncertainty and reducing that uncertainty in a particular way. This reduction requires energy. The famous principle known as Landauer limit states that erasing one bit of information necessarily generates heat. The brain does not erase information in the simplistic sense, but it constantly updates and rewrites patterns. Every time it does, entropy rises. This simple thermodynamic cost ensures that information processing is inherently directional. You can form memories only by moving forward along the path of increasing entropy. The brain can build a record of the past, but cannot build a record of the future because the very act of building a record locks the system into one historical direction. This explains why memory is asymmetrical, even though the laws of physics are symmetrical. Memory is not about the laws. It is about the physical implementation of information inside a system that evolves irreversibly. The brain uses energy, dissipates heat, and operates far from equilibrium. It is a living engine that relies on chemical gradients, ion flows, and the constant exchange of matter with the environment. These processes are irreversible. Each step creates entropy. Because the brain operates irreversibly, the mind experiences time irreversibly. The arrow of time is therefore not an illusion. It is the direct consequence of how information is physically stored. Consciousness deepens this asymmetry. Awareness unfolds over sequences of states that must be processed in order. Sensory input arrives as signals that propagate through networks of neurons. These signals depend on previous states. They modify future ones. Awareness is the continuous integration of information arriving from the senses and from within the brain itself. This integration requires a stable reference frame. The only available stable frame is the flow from low entropy states to higher entropy ones. The universe gives consciousness one direction to anchor itself. That direction becomes what we call forward in time. Even the feeling of now, the present moment that seems to move from one instant to the next, arises from information processing. The brain must continuously update its internal model of the world, comparing incoming signals with stored memories. This comparison requires time. It requires change. It requires the accumulation of records. Without these records, the concept of now would dissolve. The mind would not experience a thread of moments. It would experience nothing. Perception itself depends on the irreversible flow of information. There is another layer to this story. The brain is built from matter shaped by billions of years of evolution. Evolution itself is an irreversible process driven by entropy and selection. Biological systems survive by consuming energy, producing heat, and increasing entropy in their surroundings. Every living creature is a tiny arrow of time embedded in a larger arrow. Life cannot run backward. Evolution cannot run backward. The origins of consciousness therefore arise from processes that unfold through irreversible histories. The mind inherits the arrow of time from the biology that created it. Information in the brain also spreads and entangles, just as quantum information does. When you sense a sound or observe a shape, the event triggers cascades of neural firing. These cascades propagate, creating vast networks of correlations throughout the cortex. Once these correlations form, they cannot be reversed. To reverse them would require rewinding every electrochemical event, every molecular motion, every release and uptake of neurotransmitters. The probability of this occurring is effectively zero. The brain therefore moves forward just as entropy moves forward. The arrow is embedded in its structure. Memory also has a critical role in distinguishing past from future. The past is fixed because information about it is stored. The future is open because information about it is not yet encoded. This distinction is not due to metaphysics, it is due to information theory. A fixed record defines what has already occurred. The absence of such a record defines what has not. The brain cannot store what has not yet happened. That is why the future feels uncertain, and the past feels definite. The certainty of the past comes from stored information. The uncertainty of the future comes from the absence of that information. Consciousness experiences this asymmetry as the sensation of time flowing toward new possibilities. The alignment between memory and entropy also explains why we do not remember events in reverse order. If the universe had started in a high entropy state and moved toward lower entropy, memory would also run backward. We would recall what we call the future and anticipate what we call the past. This is not a contradiction. It is an illustration that the direction of memory depends entirely on the direction in which entropy decreases. Since the universe began in a low entropy state, memory forms in the direction where entropy grows. That direction becomes the psychological arrow of time. Information and entropy are intertwined at every scale. A gas spreading through a room gains entropy as it explores more possible configurations. A mind learning new information gains entropy as it rearranges neural structure. A collapsing star increases entropy as it transforms potential energy into heat. These processes share a common principle. They move from states with fewer possible microscopic arrangements to states with more. A brain living in such a universe must form memories in the same direction. Otherwise, consciousness would be impossible. This deep connection between physics and psychology shows that the arrow of time is not an arbitrary feature of the mind. It is a property that emerges from the way information is processed in a world where entropy increases. Consciousness cannot experience time any other way. The brain is an irreversible machine operating within an irreversible universe. Time feels as if it flows because memory aligns with entropy. Awareness rides the gradient from order to disorder. Future and past feel different because entropy makes them different. To complete the picture, we must connect all these arrows. The thermodynamic arrow, driven by entropy. The gravitational arrow, driven by structure formation. The quantum arrow, driven by entanglement and decoherence. The cosmological arrow, driven by expansion. And now the psychological arrow, driven by memory and information. Each arises from the same initial condition. Each points in the same direction. Each exists because the early universe was simple and smooth. With these layers in place, the final task is to synthesize them. The arrow of time is not chosen by law, it is chosen by the beginning. In the final chapter, we follow this idea to its conclusion. The mystery of time reaches its deepest point when we gather every thread of evidence from the universe and lay them side by side. Thermodynamics reveals an arrow pointing from low entropy to high entropy. Gravity sculpts structure from a smooth beginning and drives entropy upward through the collapse of clouds and the birth of stars. Quantum mechanics shows entanglement spreading in ways that become impossible to reverse. Cosmic expansion stretches space, cools radiation, and makes irreversible evolution possible. Memory and consciousness rely on the same direction because information can be stored only as entropy rises. Each arrow seems independent at first glance, yet they all align perfectly. They all point in the same temporal direction. They all emerge from the same cosmic origin. The laws of nature did not choose that direction. The universe did. Imagine the earliest moment of the cosmos. Not the fireball of popular imagination, but the deep structure behind it. A state of astonishing uniformity, so smooth that gravity had almost nothing to sculpt. A state with extraordinarily low gravitational entropy. A state that carried within it the seed from which every future process would unfold. That early smoothness created a slope in the landscape of possibilities. Entropy could rise only one way. The universe could evolve only along that slope. Time could possess only one arrow. From that single point of simplicity, a grand asymmetry emerged that shaped the entire history of everything that would ever exist. As the universe expanded, the slope lengthened. Tiny fluctuations grew. Clouds formed. Gravity amplified the smallest differences into vast structures. The first stars ignited and poured energy across space. Their light heated surrounding gas and carved new conditions that could never be reversed. When stars died, they created heavier elements. These elements gathered into planets. On one such planet, chemical reactions assembled into the first living systems. Life emerged from processes that depended on irreversible change. Evolution unfolded through countless generations, each leaving records of the past etched into genomes. Consciousness followed, memory grew, awareness formed. All of these developments were anchored to the same direction because they were part of the same universal increase in entropy. The arrow of time, therefore, does not arise at one particular scale. It is not created in kitchens when ice melts, or in stars when hydrogen fuses, or in quantum laboratories when decoherence spreads. It arises from the earliest moment of the universe when entropy was at its lowest. Every irreversible process since then is a continuation of the original direction chosen by that beginning. We move forward in time because the universe positioned its initial state in such a way that forward is the direction in which entropy increases. This leads to a striking realization. The arrow of time is not a universal rule. It is a boundary condition. A condition placed at the start, not a rule written into the laws. If the universe had begun in a state of maximal entropy, time would still exist as a coordinate, but no direction would arise from it. The cosmos would not develop structure. There would be no growth of complexity. There would be no memory or evolution. No future would feel different from the past. Time would exist without meaning. But the universe did not begin in such a state. It began in a state of exquisite order. This perspective reframes our understanding of the past. The past is not special because it is earlier. It is special because it contains less entropy. The future is not open because it is later. It is open because it contains more possible states. The asymmetry between past and future comes entirely from the shape of the entropy curve. That curve begins low and rises as the universe evolves. Our experience of time flowing is the subjective sensation of moving along that rising curve. The remarkable unity between the arrows also reveals why time cannot be reversed in practice. Reversing time would require reducing entropy. But to reduce entropy, we would need to move the universe back toward its original smoothness. That smoothness is impossibly specific. It is like placing every particle in the universe back into the exact arrangement it occupied at the beginning. The probability of achieving this is so low that it is indistinguishable from zero. Even the smallest irreversible event contains astronomical complexity. Reversing all such events would require unwinding the entire history of cosmic evolution. The arrow of time is not fragile. It is embedded in the deepest structure of reality. This leaves a final question. If the laws of physics contain no preference for a temporal direction, why did the universe begin in a state that supports an arrow at all? Why did it not begin in equilibrium? Why did it not begin in chaos? This is one of the most profound mysteries in science. Some theories propose that inflation shaped the early universe into a smooth state, stretching irregularities across unimaginable distances. Others propose that the state arises from a deeper principle of quantum cosmology. Still, others consider the possibility of a two-sided universe, where time flows away from the Big Bang in opposite directions, each forming its own arrow. But even with these ideas, the fundamental question remains open. Something placed the universe at a low entropy starting point. and that something is not yet fully understood. Even so, we know what that choice produced. It produced a cosmos that changes, a cosmos that evolves, a cosmos where galaxies swirl, stars burn, planets cool, and life emerges. The faint glow of the cosmic microwave background, the shimmer of starlight, the movement of tides, the ticking of biological clocks, the growth of forests, the rise and fall of civilizations, all of it traces back to the early smoothness of the universe. That smoothness made entropy possible. Entropy made time directional. Direction made memory possible. Memory made consciousness possible, and consciousness gives time its human face. When you look at the night sky, you are witnessing the arrow of time written in light. Every star is a beacon of irreversible change. Every galaxy is a monument to the rise of gravitational entropy. Every photon you receive is a message carried forward along the arrow. Your thoughts unfold in the same direction because your mind is built from the very processes that follow that arrow. The universe does not favor forward time. The laws do not prefer one direction. The arrow is not fundamental, it is emergent. It arises because the beginning made it so. The story of time is therefore the story of the universe choosing a path from a sea of mathematical possibilities. The path is not determined by a law. It is determined by the starting point. Time flows because the universe began in a state from which flow was possible. The arrow exists because entropy had room to grow. And we move along that arrow because every atom in every part of the cosmos is following the same rise toward complexity. In the end, time is not a river moving past us. We are the ones moving. We are carried by the expansion of entropy, by the unfolding of structure, by the growth of information, and by the memories written into our neural patterns. The laws do not compel this motion. The universe's initial condition does. Time does not choose a direction, but the universe does. And we, living inside its grand evolution, continue drifting along its one-way tide.